All right, guys, so in the last video, one of the things that we did was we laid down some definitions so that we can start using this new technique of circuit analysis, the mesh current method. And one of the things that I mentioned very briefly is that the currents that you've been dealing with up until now are called branch currents. And there is a distinction between these mesh currents and the branch currents, but there is a relationship between the two that's mathematical in nature as well. And I really want to bring that out and show you what that happens to be. So the next topic of discussion is on the distinction between mesh currents or branch currents, or I can also call it branch currents versus the new mesh currents. And the way I'm going to bring out the distinction is through an example. Right. Suppose that you had the following circuit. So consider the following circuit. This circuit contains one voltage source over here, providing us with V1 worth of voltage. There's a resistor R1 up here, a resistor down this way, resistor over there, a second voltage source providing us with a voltage V2 on this side. This is R2, this one is R3, and let's just finish up the circuit like this. Now, one of the things that we have to do is, before we can start doing any sort of circuit analysis, is we need to define our variables very carefully. And I'm going to take a little bit of care in defining some currents here. But before I do that, keep in mind that we do have some nodes here. I'm not going to really name them, because it's just important that you identify where the nodes are. So there's one big node down here at the bottom. The other nodes you can see there. And suppose that I were to define the following currents, right? So suppose that I actually define, let's say, a current that flows through R1 from the left to the right. Notice that this current by KCL at this node, right there, notice that this current must be the same current that flows through here as well. Now, this I1 does not go to the right-hand side and go through R2, or doesn't go down through R3. We have to define new currents there, right? So, for example, kind of at pseudo-random, I could define a current I2 flowing from there to there. Notice that it is going from this node to that node through the resistor R2. And then I would need to define another current flowing through R3. Let's just suppose that it goes down this way. I'll call this I3. And notice that it's flowing from there to there through resistor R3. And by KCL, whoops, by KCL at this, there we go. By KCL at this node, we can also deduce that the same I2 must go through there. Now, the observation that I really want to make is now we actually have currents defined through each one of these circuit elements, right? The currents are well defined. These currents, the currents, I1, I2, and I3 are what they call branch currents. They begin at a node, flow through a single element, and end in a node. They are nowhere else in the circuit defined unless the elements are in series. They do not exist anywhere else in the circuit. Now, let's contrast this with the following new way of doing business. I'm going to do the same thing with these new mesh currents. So it's going to be the same circuit. But with mesh currents. So here I'm going to redraw the circuit. We have our voltage source V1, resistor, 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 voltage source V2, and then we finish. So this is R1, R2, R3. And it should be very, very clear that we actually have two meshes here. One mesh right there, one mesh right there. And within these meshes, we can actually define mesh currents, right? So here, I'm going to define IA flowing through there, all around that mesh, and IB flowing around that mesh. Now, I made this kind of circular path, right? But keep in mind that this itself is kind of shorthand for currents flowing in the following manner. We do have a current flowing, IA flowing through there, flowing through there, flowing through this wire, and it's also flowing through this middle section. So all of these are the same IAs. And for the other one, that circle that I have IB flowing through here, through there, and it also flows through there. So notice how IA and IB are flowing along the entire perimeter of these meshes. They're not starting at nodes and ending at nodes. They're everywhere defined along that mesh. Now, there is a relationship between the mesh currents and the branch currents that we actually had previously. And I'm trying to just get rid of these. You can actually determine how the mesh currents and the branch currents are related by taking a look at superposition, right? So if you happen to take a look at the branch currents that we had previously, remember we had I1 going there, I1 going there, we had I2 going there, I2 going there, and down the middle here we had I3. Notice that I1 and IA exist along that voltage source. They match perfectly. They match not just with magnitude, but they also match with direction. So one thing that we can actually very clearly state is that I1, which is a branch current, is the same thing as IA, which is a mesh current. Right? Similarly, if you take a look at, let's say, over here, I have I2 there, and I have IB flowing in the same direction that way. It also happens to be flowing down through there. So I can also say, by taking a look at that one, that I2 is equal to IB. The only place where there's a bit of a difference between the mesh current and the branch current right now is right through this middle section. Notice that I3, which is a branch current, is flowing downward through R3. We have IA flowing in the same direction as I3, IB flowing upward in the opposite direction. So according to superposition, I can say that I3 is equal to IA minus IB, right? So in this particular case, the mesh currents and the branch currents that we've defined, there is a relationship between the two, right? But they are different, right? And we'll see in the next few videos how these can be used to great effect in order to solve and analyze circuits.